والإعدادية والثانوية العامة ومدارس اللغات والإعدادية الأزهرية والثانوية الأزهرية. تابعونا نضمن لكم النجاح والتفوق بإذن الله.
My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about laser. We'll be able to differentiate between two emissions, spontaneous emission and stimulated emission. Also, we'll try to make a comparison between the light produced by stimulated emission and that produced by, spontaneous emission. So let's get started. Laser. What's meant by laser? As a matter of fact, laser is, light amplification by stimulated emission of radiation. Once again, it is light amplification by stimulated emission of radiation. In 1917, Einstein showed that there are two kinds of emission. Spontaneous emission, and it is the rapid one, and the stimulated emission, which is the delayed one. Spontaneous emission produces normal light. Stimulated emission produces laser. So we've got two types of emission, spontaneous and stimulated. We'll start with spontaneous emission. What about spontaneous emission? The atom has energy levels. The lowest of these energy level is called the ground state. Ground state is denoted by E1. So E1 denotes the ground state, which has the lowest energy. The atom be excited to be, in one of the higher energy levels. Okay, higher energy level is denoted by E2. In front of you, we've got a diagram. To make the atom make transition from ground state into excited state, we want an appropriate photon. What does it mean, appropriate photon? We want discrete amount of energy, which is, equal to the difference between E2 and E1. When this appropriate photon falls on the atom found in the ground state, what happens? The atom absorbs this particular photon and it makes a transition to E2. E2 denotes excited state. There is a lifetime which is very short. The electron stays for a very short time. Then it relaxes again to E1 to give a photon which has an energy equal to E2 minus E1. And of course, it is equal to h nu. But there is something very important. In the atom, there are many, excited states. So the photons produced by this process have different frequencies, different energies, different wavelengths, since we have many excited states that the atom can found in it, okay? So, when a photon of the appropriate energy which is equal to E2 minus E1, which is equal to h nu, falls on an atom in the ground state, once again, what happens? The atom absorbs the photon and makes transition to the excited state. Excited state is denoted by E2. The atom, after a certain time, we call it lifetime, and it is very short time, it is 10 to the power of negative 8 seconds, the atom spontaneously, out of its own, falls back, relaxes to the ground state, and emits a photon of energy, h nu, which is equal to E2 minus E1. Okay. The emitted photon has the same frequency and energy as the absorbed photon. Okay, we have something to mention here. Your attention. A spontaneous emission is not triggered. It is not caused by an external influence. It's not triggered by an external factor, but the atom, after its lifetime is over, the atom moves out of its own accord to the ground state. Spontaneous emission is the common feature of the radiation emitted by the normal light sources. It means, yes, it is the common feature which happens in normal light sources. A spontaneous emission is defined as the emission which occurs, it is the emission which occurs when an electron relaxes under no influence of any external factors from an excited state to its initial state after its lifetime is over, is elapsed. And now talking about the emission which produces laser. We call it stimulated emission. When a photon of the appropriate energy, as I mentioned before, it is the difference between the ground state and the energy of an excited state, E2 minus E1, which is equal to h nu, h Planck's constant. Nu is the frequency. When a photon of the appropriate energy just passes by an excited atom before its lifetime is over, what happens? Okay, the photon stimulates the excited atom to relax, to fall from E2 to E1, and a photon of the same energy, which is the difference between E2 and E1, which is equal to h nu, is emitted in addition to the stimulating photon. So we've got two photons in this process, the stimulating photon and the stimulated photon. And both of them are identical. They've got the same energy, frequency, and wavelength. Okay, in front of you, we've got an atom which is previously excited. It's already excited. It is found, the electron is found in the excited state which is E2. And what happens? Stimulating photon, when a stimulating photon passes by this particular atom, okay, before its lifetime is over, it stimulates the electron, okay, to relax to E1. In this way, we've got two photons, a stimulating and a stimulated photon. The stimulating and stimulated photons have the same frequency, phase, and direction. That's to say, the emitted photon, okay, stimulated one, is in every way identical to the stimulating photon. The photons emitted by stimulated emission are coherent and collimated for long distances. We'll explain these two particular terms later on. They are highly concentrated and remain unscattered, okay, unlike the photons emitted by the spontaneous emission. Stimulated emission is the common feature of laser. Stimulated emission produces the light, we call it laser. Stimulated emission is the emission, this is the definition of stimulated emission. What about it? It is the emission of a photon under the effect of another, such that the emitted photon is in every way identical to the incident photon. Incident photon, we call it, or is called a stimulating photon. And now talking about characteristics of a stimulated emission. Once again, we'll talk about the characteristics of the stimulated emission. Stimulated emission is characterized by the emission of a new photon in addition to the stimulating photon. The emitted photon and the stimulating photon are in every way identical. The emitted photon and stimulating photon have the same phase. And now let's make a comparison between spontaneous emission and stimulated emission. So we are comparing spontaneous emission to stimulated emission. First of all, the atom in the ground is in the ground state, talking about spontaneous emission. The atom is in the ground state when the incident photon falls on the atom, falls on it. Okay? But the atom is excited and its lifetime is not over yet when the stimulating photon passes by it. Okay? This is very important point of difference. The atom is in the ground state when the photon falls on it. In a stimulated emission, the atom is excited. The atom in a spontaneous emission absorbs the incident photon and makes transition to the excited state, excited energy level. So the incident photon is absorbed in a spontaneous emission, but the atom does not absorb the stimulating photon. Talking about stimulated emission. This is another point of difference. The photons emitted by spontaneous emission have a wide range of wavelengths, wide range of frequencies, so we call it polychromatic. Poly means many, wavelengths. Chroma means wavelengths, okay? The photons emitted by spontaneous emission have a wide range of wavelengths. They are polychromatic. Photons emitted by stimulated emission are monochromatic. They are of single wavelength, just one wavelength. Photons emitted by spontaneous emission propagate randomly in all directions. They are divergent. They propagate randomly in all directions. Photons emitted by stimulated emissions are coherent and propagate in one direction. They are collimated. They are collimated parallel beam. Spontaneous emission is not triggered by external influence. The excited atom falls out of its own accord from the excited state to the ground state. But in a stimulated emission, yes, the emission is triggered by external influence. It is triggered by the, yes, stimulating photon. Intensity of the photons emitted by spontaneous emission, okay, obeys the inverse square law of light. So the photons emitted have, yes, large angle of divergence. They are divergent. Large angle of spreading. And they are easily scattered when colliding with the particles of the medium. But intensity in stimulated emission does not obey the inverse square law. That's to say, yes, intensity remains constant over long distances. So the spreading effect is nil, is zero, and limited scattering takes place. Spontaneous emission is the dominant radiation, dominant feature in ordinary light sources. Stimulated emission is the dominant emission or dominant radiation in laser sources. And now talking about characteristics or properties of laser light. First of all, it is monochromaticity. What does it mean? Monochromaticity means laser light has high monochromaticity, it has high purity of spectrum. It is almost of just one wavelength. So first of all, talking about the monochromaticity of laser. Laser light has a spectral line with a very small bandwidth, and the intensity is concentrated at the wavelength of that spectral line. Hence, laser light is highly monochromatic. Monochromatic means of just one wavelength. Unlike laser light, a selected line in an ordinary light source, so if we compare between laser light and normal light source, such as the light emitted from a gas discharge tube, it includes a wide band of wavelengths, and this explains why the ordinary color appears to have different shades to the naked eye. Second property, it is called collimation, or the light rays are parallel. Laser is a beam of parallel, yes, waves. Laser light is highly directional. So talking about collimation being parallel rays. In ordinary light sources, the diameter of the emitted beam increases with the distance, while in laser light, the diameter stays unchanged for long distances without much scattering, without much divergence. Thus, energy is transmitted without much loss. Talking about the next property, next characteristic, yes, property of laser, it is coherence. What does it mean? Yes, coherence means laser light is highly coherent, means they've got, or the photons have got the same phase. Photons of ordinary light sources propagate randomly, incoherently. They emanate at different instants of time and have inconsistent and varying phase. In laser, photons emanate coherently both in time and place, since they come out together at the same time sequence and maintain the same phase during propagation over long distances. This makes laser light very intense and focused one. And finally, the last characteristic here, it is the intensity, and it is a result of the previous characteristics. Laser light is very intense light. Photons of ordinary light sources obey the inverse square law, while photons of laser light do not. That's to say, their intensity remains unchanged for long distances. And now talking about theory of the laser action. Talking about theory of the laser action. Laser action depends on driving the atoms or molecules of the active material. We call the active material the amplifying material. So laser action depends on driving the atoms of the amplifying material into a certain situation. Into a situation, we call it population inversion situation. In this situation, your attention please, I'm talking about a situation which is very essential for laser light to be produced. We call it population inversion situation. In this situation, the number of atoms in the excited states exceeds, number is greater than the number of atoms in the ground state. This happens in a certain situation, we call it, yes, population inversion situation. And it is essential for laser to be produced. The active materials, amplifying materials used in laser are chosen because they possess metastable energy levels. So we've got something here, we call it metastable energy level. When the situation of population inversion is reached, stimulated emission becomes predominant and laser light is produced. And now it is time to define, yes, metastable state. What about a metastable state? It is a state in which electrons remain excited for a long time. It is 10 to the power of -3. Compare this figure to the normal one, which is 10 to the power of -8. And instead of -8, the electron remain excited for a time interval of 10 power -3 seconds. In certain energy levels, we call it metastable energy level. I'll explain what's meant by population inversion. So in front of you, we've got a diagram. In diagram A, which we call it normal condition, atoms are found in the ground state. Then we've got, yes, population inversion state. If you compare the atoms found in E2 to that found in E1, atoms found in the excited state and that found in the ground state, the number in excited state exceeds that in the ground state. We call it population inversion. Then, yes, then the stimulating photon acts. What happens when a stimulating photon passes by the atom which is found in this situation, population inversion situation? Okay, it stimulates more atoms to make transition from E2 to E1. Okay, so atoms falls from E2 to E1, and in this way we'll obtain laser photons of the same energy, almost of the same frequency and wavelength, and they are in phase. And now talking about the main components of a laser. Talking about components of a laser. Despite the variations in size, type, and energy in lasers, there are common components, or three common components must exist in any laser. Three common components must exist in any laser. Yes, the active medium, active material, and it can be crystalline, solid, such as in ruby laser, a semiconductor in crystalline silicon, a liquid dye, such as organic dyes solved in water, gas atoms in helium-neon laser, helium-neon mixture, and it is the type we'll study together. So it could be gas atoms. It could be, the active medium could be ionized gases. An example for this, argon in argon laser. Or molecular gases. An example is carbon dioxide in carbon dioxide, laser. Second component is a source of energy. Source of energy to excite the active medium. Okay, so the first component is the active material. The second is we need a source of energy, Okay, to excite the active medium as follows. Excitation could be by electrical energy, either by using radio frequency waves or using electric discharge under DC voltage, as in helium neon laser and argon laser. Okay. Excitation, could be done by light energy. We call this optical excitation or optical pumping. Light energy, optical energy, which is known as optical pumping. It occurs either by using flash tubes, and this happens in ruby laser, or by using a laser beam as a source of energy, and this happens in liquid dye laser. And we've got a process called pumping process. What about it? It is imparting of energy, giving the active medium energy to excite it. We call it pumping process. It is imparting of energy to the active medium to excite it. We've got also thermal excitation. In this case, a gas is strongly heated, giving the molecules or atoms sufficient kinetic energy such that during collisions with the active material is excited. And this happens in helium neon laser. Excitation could be done by chemical energy. Chemical reaction between certain materials gives off sufficient energy to stimulate atoms to produce laser. For example, the reaction between hydrogen and fluorine, the reaction between deuterium and carbon dioxide. We've got something very important. We call it resonant activity. The third major component of any laser, we call it resonant cavity. and it could be classified into two types. First of all, let's define the resonant cavity. It is the container and the activating catalyst for amplification. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.